Hello, everyone. First of all, thank you so much for coming. I just want to welcome you to the 37th annual J. Warren Perry Lecture. I am Lorraine Collins. I'm the Associate Dean for Research for the School of Public Health and Health Professions. I'd like to begin today's event by acknowledging our founding benefactors, Doctors J. Warren Perry and Albert Recate. J. Warren Perry was the founding dean of the School of Health-Related Professions, which became the School of Public Health and Health Professions, and was one of the school's most generous benefactors. He made sustaining gifts to this lectureship, which bears his name, and with his brother Charles established the J. Warren Perry Scholars Program and the Western New York Wellness Works Regional Resource Center. Albert C. Recate, MD, also played a role in founding the School of Health-Related Professions, serving as acting dean from 1965 to 1966, and associate dean from 1966 to 1974. Dr. Recate, who died in 2010, and his wife Linda have been generous benefactors to the health sciences at UB and strong supporters of the SPHHP. Gifts from the Recate family enabled the development of the school's core curriculum and continues to support the Glenn E. Gresham Visiting Professorship in Rehabilitation Science. So today it is my pleasure to introduce Dr. Larry Kenney. Just a few highlights of Dr. Kenney's career. He is the Marie Underhill Knoll Chair in Human Performance and Professor of Physiology and Kinesiology at the Pennsylvania State University. He earned his doctorate in physiology from Penn State. His research focuses on the topics of human responsiveness to exercise, heat and cold stress, along with dehydration, biophysics of heat exchange between humans and the environment. Dr. Kenney has published approximately 300 journal articles and multiple editions of 2 books. He is the primary author of Physiology of Sport and Exercise, a best-selling textbook in exercise physiology, now in its 9th edition, which has been translated into 14 languages. His research has been continuously funded by NIH from 1986 through 2015. He had one of the longest running R01 grants. Those were the good old days. And he continues to be funded by the NIH. He's been an active mentor to graduate students and postdoctoral trainees. During his career, Dr. Kenney has received numerous honors and accolades, including the prestigious Faculty Scholar Medal from Penn State for his research contributions. He served as president of the American College of Sports Medicine between 2003 and 2004 and is a fellow of the American Physiological Society. He's one of only 10 scientists who have been the recipient of honor awards from both the ACSM, the Sports Medicine Group, and the APS, the Physiological Society. He was the former chair of the Gatorade Sports Science Institute and serves on many scientific advisory panels, including Nike's Science Advisory Board. So please join me in welcoming Dr. Kenney as he presents Too Hot to Handle, Aging in the Era of Climate Change.
Well, thank you, Dr. Collins, for that gracious introduction. You're all thinking the same thing. How can a 30-year-old guy have done all those things in his career? But it really is my pleasure to be here and be able to speak to you a little bit about some of the work that we've done over the years and some of the primary work we've done over the past 5 or 6 years. So I chose this title because, number one, I'm not afraid to use climate change, even though those are bad words, as It pertains to our current funding environment. And for the past 5 years, we've really been focusing on the issue of aging, the elderly being the most vulnerable population with respect to extreme heat events. So, as you know, we live in a warming world, and you read a lot about the fact that the global climate is increasing by 2 degrees centigrade over the next 10 years, or 4 degrees centigrade over the next 30 years. And I'm here to tell you that with respect to human health, that increase in the mean global temperature really doesn't matter all that much. One of my favorite physiological experiments was done in 1774 by a guy named Charles Blagden, where he took some friends, a dog, a raw steak, and some eggs into a room heated to 260 degrees Fahrenheit. One of my discussions with the students right before I came over here was, how hot can you have people stay in your environmental chambers, and for how long? After 3/4 of an hour, the steak and eggs were cooked, but the humans and the dogs were just fine. So humans are tropical animals. We evolved from tropical climates, and we can sustain very high environmental temperatures, at least for short periods of time, provided 3 things happen. We can sweat. That sweat can evaporate, and we don't touch the hot surfaces. So the problem really isn't the mean change in climate, it's the extremes. So as that curve shifts toward hotter environments and flattens out, we have more future days of what in the past we called extreme heat, and now hotter future extreme heat days. So it's this tail of the curve that's more important, because that results in more environmental heat waves, longer lasting environmental heat waves, and more severe environmental heat waves all over the globe. And there are limits to how much heat humans can tolerate for long periods of time. Climate change is not a brand new thing. There was a paper in Popular Mechanics in 1911. I was just getting out of high school at the time. I remember reading it. And it talked about a torrid wave of unparalleled heat throughout the country, where the mercury was above 100 degrees in Western Canada, and temperatures exceeded temperatures that anyone had seen to that time. And this paper in 1911 concluded, one may well ask if the climate is not changing and getting warmer. But we didn't learn a lot of lessons from that period of time till now, until probably the past 15 or 20 years, when now all of a sudden people started to realize that this is an existential crisis and a problem for human survival. We also live in an aging world. So not only is the world getting warmer, it's getting older. So in 2030, about 16.5% of the world's population will be over the age of 60. But by 2050, almost 22% of the world's population will be over the age of 60. And in 2035, for the first time, there are projected to be more people on Earth over the age of 65 than under the age of 18. And so you combine those two things, and we definitely live in a changing world. This is a graph showing past climates and global warming projections of 1.5, 2, 3, and 4 degrees centigrade. And if we were only worried about the changing climate, these are the projected average annual heat-related deaths with each of those projected increases in global temperature. But when you add in climate and the population change, the aging population, you get an even more dire picture with larger projected increases in morbidity and mortality based on the combination of global climate change and the aging population. And so it's exponential. It's clearly an age-related condition. There are infants who die every year in hot environments, primarily those who are accidentally left in hot cars and so on. Heat-related deaths are almost unknown in children, active children, aged 5 to 14, regardless of the fact that CDC and WHO all list active children as a vulnerable population. There's just no evidence for that. In the 18 to 35-year-old age range, there are exertional heat-related deaths, and those are primarily in sports and the military. But you see this dire picture over the age of 65 with increases in exponential morbidity and mortality during environmental heat extremes. So if you dig in a little bit closer, this graph represents the heat rate death by age group during the heat dome that was in British Columbia a few years ago. And again, you can see this age bias very clearly, so that 90% of people who died in British Columbia during the heat dome over the US Northwest and that part of Canada were over the age of 60. 98% of them were in indoor environments. 93% had no air conditioning, and 56% lived alone. So most of the older people who have problems during environmental heat waves are in their homes. Very few were institutionalized because there are things in place to mitigate those problems in most cases for institutionalized elderly individuals. And a point that I'll come back to later is that more of those deaths occurred in female elderly men and women, or female elderly people, than in their age-matched men. So we've done a lot of work over the years doing basic physiology of why, as we get older, we're less able to tolerate environmental extremes. So as some examples, if you just look at sweating, if you have individuals exercise in a hot room, young individuals have higher sweat rates. Normally fit older individuals have the lowest sweat rates. But if those individuals train and become more aerobically active, or you heat acclimate them, they can increase their sweating rates. So they can adapt. However, they never get to the point of the thermoregulatory advantages of the young subjects. We've gone in and looked at why that is. There was a theory for a long time that sweat glands atrophy as the skin ages. And so we went in and we directly injected methylcholine, which is a long-acting activator of heat-activated sweat glands. And we counted sweat glands in that area and sized the sweat glands. And it turns out that older individuals activate just as many sweat glands, but each sweat gland produces less sweat. So the sweat glands get smaller and produce less sweat. We have looked at skin blood flow. And so for every increase in your mean body temperature, skin blood flow doubles essentially in young subjects. And these are just subjects lying at rest. But in older individuals, that increase is much smaller. And unlike the sweating response, this is less trainable. And we've done a lot of work over the years looking at why that is, what changes in skin as humans age related to nitric oxide, oxidant stress, and those sorts of things. So we know a lot about the physiology. Oops. Very importantly, when older individuals die during environmental heat waves, the cause of death is rarely heat stroke. It's almost always a cardiovascular event brought on by high body temperatures. So the aging cardiovascular system and the aging left ventricle really contributes to most heat-related morbidity and mortality among elderly men and women. And so for a given amount of heat stress, older men and women pump less blood from the heart, so their cardiac outputs are lower, and they redistribute less blood flow from their GI system and from their kidneys. So a normal response of a young, healthy subject, if you heat them up, is their heart pumps twice as much blood. That all goes to the skin, where it's needed for dissipation of the heat. And we decrease blood flow to areas of the body where we don't need it. And that's primarily the liver and the kidneys and the gut. Older individuals have attenuated responses in both cases. And these are healthy, relatively active, 65 to 80-year-old men and women, non-smokers, minimal medications, and so on. So all of that is the backdrop for the project that we've been doing over the last 6 years, which we've called the Human Environmental Age Thresholds Project, or Penn State HEAT. And so we set out to answer the simple question, what seems like a simple question, which is, when should we care? How hot and humid is too hot and humid, especially for older men and women? Is it 80 degrees and 30% humidity when we should start worrying? Is it 90 degrees and 10% humidity? And so we wanted our studies to have external validity. We wanted to relate to actual environmental heat events. So clearly we wanted to study aging. We wanted to emphasize indoor morbidity and mortality because that's where most of it occurs from an epidemiological perspective. And we wanted to test these subjects either at rest or during activities of daily living. Because when there's a big environmental heat wave, your 70-year-old grandmother probably isn't out on a jog around the local golf course. But she is probably in her home cooking and cleaning, preparing meals, and so on. So to try to accomplish that goal, we recruited a large number of men and women. Initially, we compared 18 to 36-year-olds with 65 to 100-year-olds. And then as the project moved forward, added in that middle group of 37 to 64. We tested people across a large environmental range of about 90 to 131 degrees Fahrenheit and 10 to 80% relative humidity. And so all of those age groups, we tested in our environmental chambers, people carrying out activities of daily living or having metabolisms equivalent to what they would have if they were doing activities of daily living. Our young participants, we also did some very slow walking, light exertion. And then all of our older participants, we retested at seated rest. And we additionally collected data using exactly the same protocol in Sydney, Australia, and in the Netherlands for rigor and reproducibility to say, do we get the same threshold values there that we do here? So we have two fairly large, fairly sophisticated environmental chambers, and we can control those environmental chambers in terms of both temperature and humidity. So in some of our studies, what we did was we kept the temperature constant, in this case, 34 degrees centigrade, which is about 92 degrees Fahrenheit. And the subjects were in the chamber, either doing activities of daily living, resting, or walking. And after 30 minutes, we started increasing the absolute humidity of the chamber in stepwise fashion. This is an example of one of our seated rest studies. Subjects ingested a telemetry pill to monitor their core temperature a couple hours before the experiment. And this is the type of response that you see with respect to their core temperature. It initially goes up, it levels off, and then at some critical combination of temperature and humidity, it can't be maintained anymore and starts to increase. And interestingly, if you look at their heart rate, the same thing happens, but it happens earlier in the protocol. So the increase in heart rate or the onset of cardiovascular strain comes before their loss of ability to maintain their body temperature. And so if we look at the temperatures and humidities where that occurs, we can come up with critical vapor pressures, critical humidities for both temperature and heart rate. So in this case, for this subject, that one point beyond which he can't maintain a constant core temperature and is in elevated danger is 93 degrees and 66% humidity in this particular test. We do the same sorts of tests in hot, dry environments where we keep humidity constant and increase the temperature. We collect more, that's our main interest outcome. What is that critical environmental limit? But for those of you who work in temperature regulation, we collect a lot of other data from which we can calculate things like sweating, maximal sweating, efficiency, maximal wettedness, how much of the skin is wetted with sweat at any one time. And that allows us to model other conditions in addition to the ones that we measure. So here's an example of the protocol I just showed you. And in this case, that test was done at 34 degrees. And we have a mean data point for the subjects that we tested where that break point occurs, where things start to become unsafe, that's at about 80% relative humidity. We do that at a number of different temperatures where we're changing the humidity, and then we do that at a couple different humidities where we're changing the temperature, and you get a series of data points that are very labor intensive to get, but they look something like this. And they form a curve. And that curve is the upper limit of heat balance. All of the temperatures and humidities below that line we call compensable heat stress. So people can maintain their core temperature. It's a little bit elevated, but they can maintain their core temperature for long periods of time. Everything above those combinations of temperature and humidity we call uncompensable because you're gaining and producing more heat than you can get rid of. And so your body temperature is going to continue to rise consistently and constantly over time. And we were kind of going back and forth about what to call this, since people don't know compensable and uncompensable. And a friend of mine and colleague at Arizona State, Jenny Vanna, said, that's livable. You can do activities of daily living. You can continue to carry out daily life for relatively long periods of time. So livable environments, unlivable environments. And where that curve shows up changes with how much activity you're doing, the clothing you're wearing, how much air movement there is. And then we looked at a lot of physiological characteristics. Heat acclimation shifts that curve to the right. So more livable environments if you get acclimatized to the heat. But our interest, of course, was in the issue of age and aging. So one of my recent students, Rachel Cottle, did a paper where we looked at all of our experiments And we looked at this relatively flat portion of the curve. And in a worst case scenario, if you start out with a body core temperature of 37 degrees and 40.2 degrees is one of the thresholds people use for the onset of heat illness. If you look at projecting that out, this is a 90-minute experiment, but if you project that out to how long it would take to reach 40.2, the mean is 36 hours. So in those livable conditions, you can keep doing what you're doing for a long period of time with some variability. In those unlivable conditions, it comes to about 4 hours, 4 to 6 hours, essentially. So that doesn't mean everybody's going to die in 4 to 6 hours. It means they need to change what they're doing, change their environment, do something differently. And then Rob Mead in Glenn Kenney's lab in Ottawa, just to validate this, did a 9-hour mini heat wave exposure showing the same thing, that if you're in that unlivable area, your body core temperature is going to keep rising, livable and control, no heat whatsoever. So over the past 6 years, we have done 558 3-hour experiments in the environmental chamber. And we've tested 151 men and women, enough to look at gender effects, sex effects. And we did, as I said, young subjects, middle-aged subjects, and older subjects. So we feel like we have a fair degree of robustness and enough subjects that we can not only look at mean responses, but things like the 95% confidence interval. If you want to protect 95% of those people over the age of 65, where does that line fall? So this is what those critical environmental limits look like for young men and women. And what I've done here is I've drawn this line that separates the green, livable, safe environments from the pink, unlivable environments. And I've drawn that at the 95% confidence interval, the lower 95%. So these combinations of temperature and humidity are relatively safe, where these combinations of temperature and humidity are relatively unsafe. And you can see that if you start doing more activity, walking around the block, that green portion gets smaller and the pink portion gets larger. So fewer safe environments, which makes a lot of sense. So when we started to publish this information, especially during the summer months, we would get calls weekly, daily from reporters, from people looking for news articles, the BBC, the New York Times, the Center Daily Times of State College, which is a big one. And everyone said the same thing. That's really good. I see that you've put these things together, these graphs, but just tell me a single number. Like, how hot's too hot? Is it 90 degrees? Is it 100 degrees? And obviously, it's some combination of temperature and humidity. And then they'd say, well, what about the heat index? That's the one thing that everybody knows in the United States. So the heat index is defined by the National Weather Service of how hot it feels when you combine temperature and humidity. And the key wording there is how hot it feels. So the heat index is a perceptual value. It's how hot it feels to you at that given time in a hot, humid versus a hot, dry environment. And so this red portion is the extreme danger part of what the National Weather Service tells you about the heat index. Then danger, extreme caution, caution. So if you take our younger subjects who are just doing activities of daily living, doing very little, our data lines up really well with the National Weather Service. But if they start walking, that curve shifts. And the more activity they do, the more that curve shifts to the left and becomes less useful. And when you think about it, that makes a lot of sense. Because if your measure is based on how you perceive the environment, if you're just sitting there and somebody says, how hot and humid does it feel? That's all you're thinking about. If you're doing a lot of activity, if you're in an occupational heat stress setting or you're an athlete, you have a lot of other things. It's much harder to reconcile how hot you feel with the impact that environment is having on your body. And so the heat index doesn't really work very well as a physiological measurement. Which brings us to something that does work fairly well, which is something called wet bulb temperature. So wet bulb temperature, which were those curved lines I showed you on those previous temperature humidity graphs. If you take a typical dry bulb thermometer and you hold it outside, that's the temperature of the air that we're used to seeing. If you take that same thermometer and you put a wet cotton wick over the bulb, some of that water will evaporate. And the more humid it is, the less of that water will evaporate. The more dry the air is, the more will evaporate. And so in drier air, there's a bigger difference between these two temperatures. At 100% humidity, there's no difference because there's no evaporation. And so wet bulb temperature, it turns out, if you really want that single number, is a valuable tool, especially for indoor environments, because it combines the effects of air temperature and humidity and air movement to some extent. So these are the critical environmental limits that I just showed you for younger subjects. Here's that line, and these are the confidence intervals. And these lines are the wet bulb temperatures. And you can see that that line, especially in humid environments, approximates a wet bulb temperature for young subjects of about 31 degrees C. So a wet bulb number of 31 degrees C, which is about 89, 88 degrees Fahrenheit, as long as the humidity is over about 50%, that's a pretty good single number to use for safety because it combines temperature and humidity. It doesn't work very well in Arizona, where it's hot and dry. Works really well in Florida. So when you look at where those temperatures, those wet bulb temperatures of 31 degrees, which we deem as the critical environmental limit, have occurred over the world in the past 5 years, you get a map that looks like this. Primarily occurs along waterways because hot air holds more humidity. So primarily along areas of water, not so much in deserts. There was a paper in 2010 that projected that that critical environment where everybody's going to die in 6 hours is 35 degrees wet bulb temperature. 35 degrees wet bulb temperature hasn't occurred anywhere on Earth. But people are dying during environmental heat waves. So a 31 degree critical environmental limit, wet bulb temperature, makes a lot of sense. So if you look at, I'm still showing you data from young, healthy subjects. I'm going to get to the older subjects. But if you look at hours per year spent in unlivable heat, and you look at a climate change of 2 degrees, 3 degrees, 4 degrees mean global temperature, you start to see these patterns emerge in different parts of the world, from South Asia to East Asia, not so big a problem for North America, for young, healthy subjects. But you can see it obviously increases with bigger climate change projections. It occurs around areas of water. The Indus Valley in India is one of the biggest areas. And this is the projected population in those areas in the year 2050. So those same areas that showed up on that previous map of unlivable hot hours are also the parts of the world that are projected to increase their elderly population the fastest. And unfortunately, it also represents some of the typically lower middle income countries in the moist tropics and subtropics. So we have this dire situation coming together of higher heat and humidity, more older, vulnerable individuals, and especially in lower income, lower socioeconomic parts of the world. Global exposure, this is a paper we published in PNAS. If you looked at prolonged unlivable heat for a week, we're talking with a 4-degree increase in climate, we're talking about 3 million people 3 million young people being exposed to unlivable heat for at least a week. 1.5 billion being exposed to that unlivable heat for a month. And then 500,000 people, 500 million people for 3 months. So I'm going to shift now. That's the best case scenario that I just showed you. Those are young, relatively healthy individuals. But I preface this by saying that people over the age of 65 are the vulnerable population of interest. And so these are those same critical environmental limits that I showed you for young men and women. And this is what it looks like for men and women over the age of 65. Obviously, fewer livable combinations of temperature and humidity. The variability, any of you who have done aging research of any type in any discipline know that as we test older subjects, there's always a lot more variability around the mean than when we look at younger subjects. And so an environment that's 95 degrees Fahrenheit and 60% humidity is okay, livable for an 18-year-old, but now unlivable, a continuous rise in core temperature for that 65-year-old. Move from Florida to Arizona, 104 degrees and 35% humidity, same thing. What's relatively safe for the young individual, now in that red zone for the older individual. And again, we can look at those lines as critical wet bulbs. That 88 degrees for younger subjects is now 82 degrees. So another issue related to talking to reporters and the popular press and lay people about this is everybody said 82 degrees, it's always 82 degrees. But remember, that's 82 degrees wet bulb temperature. That's 82 degrees and 100% humidity. So what that corresponds to, for example, for younger subjects would be 90 degrees and 90% relative humidity, or 108 degrees and 45%. 90 degrees and 75% humidity for the older subjects, and 108 and 35%. And so all of the reporters who said, in Philadelphia last year, we had a wet bulb temperature of 92. And we said, no, politely, you didn't. That was your dry bulb temperature. So the idea is to use these environmental limits as more accurate, more empirically derived upper limits for safety in occupational settings, in homes for the aged, in public service announcements for older individuals who might be living alone, and so on. Another way to look at this is this compensability curve. So you're probably all familiar with survivor curves. So in the case, this is not survival, but this is the percent of our participants who are able to maintain their core temperature and not be in a danger zone. So if you look at young subjects, that's the blue line. Older subjects, the dashed line. And so if you take an environment like 81 degrees Fahrenheit and 60% humidity, and people are doing activities of daily living, 100% of the young subjects were able to do that while maintaining their temperature, but only 60% of the older subjects were able to do that. So in 2022, there was a huge environmental heat wave in India, Pakistan, the Indus Valley. And so these red dots represent areas of India during that heat wave, during that March to May period of 2022, where the critical environmental limit was exceeded for young, healthy subjects, young, healthy men and women. If you look at older men and women, now it's most of India, Pakistan, that part of the world. So it makes a big difference in terms of trying to plan for heat waves in the most vulnerable populations. So in our younger subjects, we looked at, does sex make a difference? Doesn't. Does VO2 max, aerobic fitness, make a difference? It doesn't. Does obesity make a difference, or body size? It doesn't. Because this is really biophysics. And as long as the young people can sweat enough, everything evens out in terms of those other characteristics. But when we look at our middle-aged and older subjects, now age and sex are specific and significant predictors of what those critical environmental limits will be. M just stands for metabolism. And so in our older subjects, age and sex together explain about 35% of the variance in those critical environmental limits. Older women are at the most risk, much more than their age-matched men in those environments. And again, there's no significant effect of these other types of influences of sweating and skin blood flow. So women are more vulnerable. And again, here's that same sort of compensability curve. And what I'll call your attention to is the fact that the older men, and this is, the top one is a warm, humid condition. The bottom one is a hot, dry condition. The older men are shown here in the blue. The older women are shown here in the red. And then middle-aged women have almost the same curves as the older men. So the loss of the ability to regulate your body temperature in different environments declines much more rapidly over the age span in women than it does in men. Starts in middle age. So middle-aged women's risk is similar to that of older men. Older women are at the highest risk. And so loss of that thermal compensation starts to occur in women during midlife. So if you look at it across the entire lifespan, at least 18 to 92 in our subject pool, you see the open circles are the men we've tested, most of them. These haven't been updated since the publication. The pink filled circles are the female participants that we've tested. And you can see in both cases, there's a decline with aging that's got some variability. Seems to be curvilinear in warm, humid environments and a little more linear in hot, dry environments. But the interesting thing to us, and what we're continuing to look at, is if you just look at the women who have been in our study, the decline in those critical environmental limits, which is a measure of kind of overall thermoregulatory capacity, starts to decline right around age 50, which I'm sure has you all thinking, what we were thinking is it age? Is it menopause? Is it the menopausal transition? Is estrogen protective, and then the lack of circulating estrogen less protective or non-protective when we get beyond that about 50-year-old age range? I don't have the answer for you, but I can tell you that one of my PhD students, Olivia Leach, just got an NIH grant to look at that specific question. And so, as you all know, if you look at years around menopause, prior to menopause, FSH, follicular stimulating hormone, follicle stimulating hormone, is relatively low, starts to increase during the perimenopausal period, and then is high throughout menopause. Whereas estrogen is high and circulating, of course, until perimenopause, and then decreases and is relatively low subsequently. So what Olivia decided to do is to take, excuse me, take a relatively narrow age range of women. In this case, so far, she's tested a group age 42 to 58. We're testing and comparing a group of those women during late premenopause. So this is the part, perimenopause, where there's symptomology, hot flashes, night sweats. So these are women who are still having regular menstrual cycles, but are within that age range. And a group of early postmenopausal women who no longer have regular menstrual cycles or report any menstrual cycles, but who haven't aged beyond that so that it's become more chronic in its appearance. So she's comparing those two age groups. She's taking the premenopausal women and for a short period of time giving them a drug called elagolix. Elagolix blocks GnRH, gonadotropic releasing hormone, and so it knocks down estrogen. So she's making the premenopausal women postmenopausal for short periods of time. And this is a relatively fast-acting drug. Within 24 hours, estrogen drops. She's taking the postmenopausal women and adding back estrogen. So she's making the postmenopausal women premenopausal in quotation marks. And so in doing that, trying to separate what may be the beneficial effects of estrogen from the detrimental effects of aging. So these studies are ongoing, and hopefully if I get a chance to come back in a few years, I'll let you know how things look. So if you look at the US, this is US aging and global warming risk projections. And the colors represent annual hot days in a year. These are defined as at least 8 hours of temperatures over that critical environmental limit. And you can see the pink, the hottest colors, are 90 days out of the year with at least 8 hours of uncompensable, unlivable heat stress. These graphs are resting conditions for older individuals. This is all age-related, all aging data, people over the age of 65. And you can see that even at rest, with a 4-degree increase in global climate change, we're talking about areas of particularly the Southeast and a little bit in these warmer, hot, dry environments in Arizona and New Mexico, California, with 30 or 45 up to 60 days of the year in that unlivable condition. Now, if you go from just sitting there to moving around and doing activities of daily living, now this part of the country is looking at 90 days out of the year under those unlivable conditions. And if you look at the population growing over the next several years, again, it's a double whammy because those are parts of the country with the largest population increases in older men and women. Globally, you get the same kind of look. These are, again, annual hot hours through the course of the year. Pink is over 2,000 unlivable hours. And you can see with a 3-degree increase in climate change, those same parts of the world that are going to be most at risk. When you increase that projection to 4 degrees, and by the way, we've already passed 1.5 degrees. Now you get increases in that 2,000 hours a year range in some parts of the world. Again, once you start talking about just being able to do activities of daily living, now it becomes even more dire. And again, these are the elderly population projections around the world by 2050, which is right around the corner. And you can see those are the same parts of the world with growing elderly populations. So these are new data we've just submitted, looking at those sorts of projections again in conjunction with our biometeorology colleagues. Global warming levels on the x-axis and populations in the billions that will be exposed, in this case, to at least 180 hours of unlivable heat annually. And you can see blue are the young subjects, middle-aged subjects, the red are the older subjects. So we're talking about here with 4%, over 1 billion people. But when you look at it as a percent of the population, now we're talking about 60% of the elderly population. So, as all of you are well aware, we live in interesting times in terms of being able to do this type of research. And I was at a conference in Europe, and I woke up one morning to see this news announcement, which has continued off and on since then, that NIH cancels climate and research, health research grants. And so we, like all of my colleagues and a lot of people in this room, have had to pivot and change wording to artificially talk about climate change and health without saying climate change and health. We're doing some of that type of work. We've pivoted to some industry sponsors. Moving forward, we're going to do more occupational critical environmental limits because, again, farmers, construction workers, it's an aging workforce, and those are people who can't afford not to work under these conditions. And so we're going to look at what those environmental limits are, the impact of things like heat acclimation and hydration of different types. So this is the primary team that have done all the work. Lacey Alexander's my former student and co-investigator. We have a cardiologist that screens all our subjects, postdocs, our nurse coordinator, our PhD students. And then we've also had great collaborators. I mentioned that we were collecting data in the Netherlands and in Sydney, Australia. Matt Huber is a climatologist at Purdue. Chin Kong is at Stanford. He's the one who does all the heat projections. So it's really been an interesting team effort where I've learned a lot about projections and biometeorology and things moving forward based on the only data set that I know of that's empirically looking at what those cutoffs are, what those thresholds are, not just guessing, not basing them on how hot it feels, but actually testing large numbers of subjects multiple times to see where they actually occur in living human beings. So I'll stop there, and I'm happy if there's time to answer any questions.